Geometric series. A geometric series is the sum of the terms of a geometric sequence. So a sequence, the terms are separated by commas, and then into a series, we replace the commas with pluses, so we're adding the terms. So in this term, the sequence, the first term is 3 and the common ratio is 2. This leads on to some additional formulae. Here you can see this is a commonly used formula to sum the first n terms of a geometric series, and we tend to use this one if the value of r, the common ratio, is less than 1. If the common ratio is bigger than 1, we use the second one. However, in reality, either can be used and we'll get the correct answer. Next, we're going to prove the summation formula for the sum of a geometric series, letting Sn represent the sum of the first n terms, which is equal to the first term, plus the second term, plus the third term, all the way up to the nth term, which is ar to the power of n minus 1. Now, I'm going to use a little technique here. I'm going to multiply both sides by r, which then gives me ar squared, ar cubed, and the final term, the ar to the n minus 1, is now ar to the n. I'm going to label this first line 1, second line 2. So now, if I do line 2, take away line 1, I'm left with r Sn minus Sn on the left hand side. Now, what you'll realise, hopefully, is that these terms will all cancel, leaving us with ar to the n minus a. Now to factorise, Sn r minus 1 equals, making Sn the subject, and here you can see we have the summation formula. Had we done 1 minus 2, then we would have had Sn minus Rsn is equal to a minus ar to the n, because all the other terms would cancel out. Again, factorising. Which would then give us Sn is equal to which, as you can see, is the alternative. So in fact, example 13, here we want to find the sum of the following geometric series. In part A, we can see that the first term is 2, and the common ratio is equal to 6 divided by 2, which is 3. We could check that by doing 18 divided by 6 or 54 divided by 18. Now we want to find the sum of the first 10 terms. So using our formula from above, we know a is 2. Now we want common ratio, which is 3 to the power of 10 minus 1 divided by 3 minus 1. So on our calculators, quickly doing this, gives us an answer of 59048. Moving on to part B. In part B, a is equal to 1024, and the common ratio is negative 512 divided by 1024, which gives us a common ratio of -1/2. Now, in this one, we don't know how many terms there are, so we need to figure out how many terms there are. In this one, remember, the nth term is AR to the n-1. Well, we know the last term is 1, so 1 is equal to 1024 times -1/2 to the power of n-1. Let's go through the process here. 1 divided by 1024 is equal to -1/2 to the power of n-1. Now here, we could go down the logarithm route to solving this. However, I recognise that 1024 is actually 2 to the power of 10. I can also rewrite the right hand side to be -1 to the power of n-1 using laws of indices over 2 to the power of n-1. Now, -1 to the n-1 must be positive, so therefore 2 to the 10 is equal to 2 to the n-1, so therefore n-1 must be 10 and n must be equal to 11. Now we can go back to solving the question. So now we know that A is equal to 1024, the common ratio is -1/2, and there are 11 terms. So the sum of those 11 terms is equal to 1024, 1 minus the common ratio to the power of 11, all over 1 minus the common ratio. Taking our calculators, being careful to type everything in with brackets, gives us an answer of 683. Example 14. Here we want to find the least value of n such that the geometric sequence is a geometric sequence because it has a common ratio of 2, as we can see. So writing that down, A is 1, R is 2, and we want to know when does it exceed 2 million? That is, when does the sum? So remember, Sn is equal to A R to the n-1. So, filling these terms in, 1 is A, 2 to the n-1 over 2 minus 1, and we want to know when is that bigger than 2 million. So, simplifying that gives 2 to the n-1 bigger than 2 million. So 2 to the n is bigger than 2,000,001. Taking logs of both sides, at this point the n can go in front, meaning we want to know when n is bigger than log of 2,000,001 divided by log of 2, and log of 2 is positive, so we don't need to worry about changing the sign. So we want to know n is bigger than, using our calculator, to get an answer of 20.931. Therefore, n must be equal to 21. So the least value of n is 20.